So we're going to be looking at pulleys, and this is effectively an extension of work we've done on connected particles. So the idea is you've got two objects connected by a string, potentially, and that string is then wrapping itself around what we call a pulley. A pulley, might literally be an actual pulley system, a sort of rotating, cylinder on a hinge, or it could just be a fixed point which acts as a sort of pulley point, whereabouts the string is wrapping itself at an angle around that point. And by and large, a lot of the calculations are the same, but there's a few extra little things that we have to look out for. Okay, so let's first off just remind ourselves, if I have two objects, two particles, and they're connected by a string, and then let's say I'm going to put my hand on this particle and I'm going to drag it along to the right. Okay, so you imagine I'm dragging that particle to the right. What's going to happen? Well, this string is going to stay taut, and this particle on the left is also going to be dragged to the right at the same speed or acceleration. The forces on the string are then a force going inwards here, T, and a force going inwards again towards the center of the string, T. Okay, and then obviously if I'm pulling the the rightmost object here, I must be pulling it with some force, let's say F. Okay, and that might be the full force diagram. Okay, disregarding gravity and things like that. But the key thing is we've got these two forces here on either side of the string, and they are the tension. Okay, so let's see how that then works in the context of a pulley. So a typical kind of pulley system you might see is something being held over the edge of a sort of cliff or a table or something like this. So let's say this is the edge of some table, and then at the end of the table I've got a sort of circular pulley. Okay, and then I've got a blue object again here, and another particle here, and again they're going to be connected by a string. So the string connects one particle, goes to the pulley, wraps around the pulley, and then comes down like this. Okay, and it'll usually be at right angles. Technically it doesn't have to be at right angles though. A pulley can deform the string in whatever way. The fact that this is at a right angle here is just a consequence of the fact that the surface is at a right angle to the direction in which gravity pulls this object here. Okay, but you could imagine systems of one, two, or more pulleys in which the strings are not necessarily at right angles. Okay, and then let's think about the tension. This is how the tension works in this case. You will again have tension here going effectively what I call inwards, so away from the edges of the string, away from the ends of the string. And at the pulley you will still have tension as well. So if you imagine, imagine this wasn't a pulley, imagine it was your hand here. I'm sure you could visualize that imagine that you're experiencing a force. The string is in some sense pushing on the pulley, and what's actually going on is you just have tension again on either side of the pulley in this fashion, okay, directing itself away from the pulley. And you can sort of imagine then there's kind of a resultant force actually. What in this scenario is the resultant force on the pulley, do you think? Well, remember, to find resultant force we connect together arrows. So let's say this is my down T and this is my left T. Okay, so we've got the two T's. These are the forces sort of acting on the pulley, or at least the ones caused by the string, and you've got a resultant force of this. Okay, so in some sense you've got the string, the green string is in this blue arrow direction acting on the pulley. So it's sort of pushing it into the edge of the table, and of course the pulley's then pushing back, and that's why the pulley doesn't move. Okay, but the key takeaway is this: tension acts sort of inwards on the ends of the string, and at the pulley you've got the tension acting away from the pulley. And all of these 4 tension values are exactly the same. So let's look at our first example. We've got 2 particles with different masses in the ratio 2 and 3, 2m, 3m. We've got a light and inextensible string, has no mass, it doesn't stretch. It passes over a small, smooth, fixed pulley. Again, all of these little qualifying words, they're there for a reason. Small, so that you don't have to think about the size of the pulley as affecting the angle of the string. Smooth, so that you know there's no friction. And fixed, so you know that the pulley's not going to be moving around. It's just in a single position in space. And the masses hang with the string taut. The system is released from rest. Okay, so very importantly with these pulley kinds of questions, you need to draw a diagram. So let's draw the pulley. We've then got a string which is effectively wrapping around the pulley, and then we've got 2 objects hanging on the end of it and each end of the string. Let's call that one P and let's call that one Q. And I'm just going to write here P has a mass of 2m and the Q has a mass of 3m, just so I don't forget. And of course I did say, you know, the pulley is meant to be small, so according to the model really, you know, this yellow circle is infinitely small, and you know the 2 green strings are the 2 parts of the same green string. They kind of coincide with each other, but you know, obviously we wouldn't be able to draw that very easily and label the forces accurately. So we draw it like this, but the principle remains the same. So now let's label all the forces. Tensions here, tensions here, there's tension here, tension here, and there's weight. The weight of P is, let's be careful here, 2 times m, that's the mass, times g. And Q is therefore 3mg. And that's all the relevant forces. In fact, that's all the forces in the system. Okay, so now let's look at the question itself. Part A, write down an equation of motion for P, and second part, write down an equation of motion for Q. Okay, equation of motion means we're doing F equals ma. So let's see, for P, F equals ma, and we need to pick a direction, don't we? Are we talking about up or down? So let's say, for example, up is positive. Okay, in fact, yeah, let's note it on the diagram itself. I'm going to take up as positive. Okay, and then here I'm saying I'm resolving forces vertically. So what forces have we got on P? We've got T going up and we've got 2mg going down. Those are the forces on P. So then that gives us T up minus 2mg down equals its mass, which is 2m, times its acceleration, which we don't know, is a. And then we've got Q. Let's look at F equals ma there. Let's resolve upwards again. Resolve vertically. Up is positive, so now let's be careful here. Yeah, we've got T minus 3mg equals 3ma. I said be careful, we didn't need to be particularly careful. It's fairly self-explanatory at this stage. And yet, I take that back. This A, acceleration, we've got to be careful here because are P and Q accelerating at exactly the same rate? Is their acceleration the same? Well, they're connected. So if Q is not moving, P is not moving. If Q is going down at, say, 2 meters per second squared, then surely P is going up at 2 meters per second squared. So the magnitude is the same. The magnitude's the same. But what's not the same is the direction. If Q is going downwards, P is going upwards. So if we arbitrarily call P's acceleration A, then consequently Q's acceleration going down will be minus A. Therefore this A over here should be a minus A. So I'm going to introduce a minus sign here. So it's minus 3ma. Okay, that's very important because otherwise, you know, these A's will not correspond to each other properly. Now at this stage I can say these A values are the same, but without the minus I can't, because we have to take the direction into account if we're going to claim that A represents you know, the same value. Okay, so we've got a nice system of equations now. Now let's take a look. Find the acceleration of each mass for part B. So as we said, we're going to get the same value, but for one of them it'll be positive, one will be negative. So we're going to have to solve our system of equations. Let's make some space and give that a go. So to find this acceleration, we're going to cancel out these t's. So let's do one equation minus the other. I'm going to go for top equation minus bottom equation. So I'll have t minus t is 0, minus 2mg minus minus 3mg, and 2ma minus minus 3ma gives me 2ma plus 3ma. This implies mg equals 5ma, and now our m nicely cancels, showing that the ratio of the masses is not even relevant to how fast they accelerate, and that gives us A equals g over 5. That's a g, not a 9. G over 5. Now that's the magnitude of the acceleration, right? In our case, we're defining up as positive. We've got that P's acceleration was A, and Q's acceleration is minus A, which we implicitly used here. So therefore, we should write this properly. The acceleration of each mass, P, it's 1/5 g, and for Q, it's minus 1/5 g, taking up as positive. Okay, just to be clear there. Okay, so, you know, depending on how picky the question might want to be, if it said the magnitude of the accelerations of each mass, they're the same, but they are going in different directions, clearly, from the way the system moves. Cool, all right, part C. Find the tension in the string. This comes easy now. Effectively, this is simultaneous equations with two unknowns, where we don't know the A or the T. And the M we technically don't know, but it's irrelevant. So just plug in your A, which is 1/5 g, into either one of these equations and you'll end up with the answer. So let's pick, for instance, this one. So that gives us T. Let's bring the 2mg to the right hand side. And we know that A is 1/5 g, so this becomes 2/5 mg plus 2mg. That's 12 over 5 mg. And if you want to, you can take a moment and also try the other equation, and it should work in both cases. If I replace this A with minus 1/5 g, you should end up with the same answer. Or I should say, sorry, 1/5 g in this case. Yeah. Cool. 12 over 5 mg. Okay, part D. This is really easy. Find the force exerted on the pulley by the string. So look at the diagram and remember what I was saying about really the pulley is kind of infinitely small, and these two parts of the string, these two green parts, are kind of in a line with each other in reality, and these two particles are also like infinitely small dots, but we've drawn it this way. However, the point is that these two forces here, these two red T's, they're both the string pushing on the pulley. So therefore, what's the total force of the string pushing on the pulley? It's just going to be 2t downwards, right? So now that we have t, the tension in the string, we just double it, and we have 2t. And that will be the answer to part D. What's the force of the pulley? Sorry, what's the force exerted on the pulley by the string? So it's 2t, and that's equal to 24 over 5 times m times gravitational constant g. Okay, and then part E, find the distance moved by Q in the first 4 seconds, assuming that P does not reach the pulley. The reason it tells us assume that P does not reach the pulley is because, of course, if P ever gets to the pulley, then we're suddenly in unknown territory, because, you know, it all gets a bit funny, doesn't it? The object will sort of wrap around the pulley and then fall down. We don't really get to that sort of stage. The particle itself won't interact with the pulley. It'll always be the string. So it's given us that out. Assume that P does not reach the pulley. How far does P move? This is just SUVAT, nice and easy. So taking up as positive, what's the initial speed of P? System is released from rest, so it's 0. The acceleration of P, if I'm taking up as positive, that's my 5th g. 4 seconds is what we've been told is the time, so now we just want to look for S, and therefore we've got S equals ut plus a half at squared. When u is 0, this simplifies the formula to this, and therefore we're going to have a tenth of g times 16, which is equal to 8 over 5 times g, and that's the distance moved in the first 4 seconds. Probably then we also want to just briefly say what this is as a decimal, since we are talking about a distance. Using g is a bit meaningless. It's about 15.7 meters, so presumably quite a long system then. 15 meters, that's quite high. That's a multi-story building. And then finally F, state how you have used the fact that the pulley is smooth in your calculations. It's quite simple. We have assumed that the pulley is frictionless, and therefore the tension throughout the string is the same. Specifically, this T here of the string pulling P is going to be the same as this T here of the string being Q, and that's permitted by the fact that the pulley is smooth and therefore allows the string to maintain the same tension throughout. Okay, so now our second example. 2 particles, masses 0.4, 0.8. A string connects them. Particle A is on a rough horizontal table, and it's 4.5 meters from a small pulley, small smooth pulley, which is fixed to the edge of the table. The string passes over the pulley, and then the other particle B is hanging at the end of that string, and it's 0.5 meters above horizontal ground. The table is rough. We did say that, didn't it? Yeah, it's rough here, so that makes sense that therefore there'd be a frictional force, and it's of magnitude 0.08 g, and that frictional force acts against the motion of particle A, which is sitting on the table. So that's all set in place, and then the system is released from rest. It's let alone to do whatever it does, and we're then going to find out what happens. So first things first, let's draw the diagram. There's our table and pulley. There's our particles with the strings connecting them, and then the final thing is the distances. So this part here is 4.5 meters, and this gap, isn't it? This gap from top to bottom between where this particle is and the ground, that's 0.5 meters. Oh, in fact, well, we don't have to draw it to scale, but that gap is actually quite a lot smaller than that distance. So let me just redraw that slightly. Okay, that looks a bit more realistic. So there we go. We've got the 2 objects and the distances marked. Should also then just actually mark this one's 0.4 kilograms. That's A, and 0.8 kilograms is B. Marking on the forces. We've got tension, 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 and tension. We've got the gravity induced weight of this object here, that's 0.8 g. We've got the gravity of this particle here, that's 0.4 g. We've got the reaction force of A, which is also 0.4 g, because we know it's not sinking into the table or flying up in the air. And we've additionally got a resistive force of friction on this one, which is 0.08 g. Is that everything? I believe it is. Yeah, that's all the relevant forces. Okay, so this time I'm going to solve it using a bit of a trick, which could also have been used for the previous example as well, in fact. And you can always go back and see if you can make the previous example make sense using this method. The method is as follows. Consider this string, which is effectively in two different directions at two different points. Consider it as one single string effectively going horizontally the whole time. So imagine, the string has two ends, so there's a clearly defined direction on anything that's going along the string. It's either going left or it's going right. Yeah. So if I say I'm going to resolve forces going right on the string, okay, or just generally I should say all forces that are horizontal, okay, then considering horizontal forces, what do we have? Right, we've got 0.08 g, that's going left. So let's say 0.08 g. Then we've got t here going right. So add t. Then we've got this t here going left. So we can take that one away. It's going to cancel. And now imagine that you're just running along this string, which is going along the pulley. So from left to right, what have we encountered? The 0.08 g, the t, we keep going, the t, and then if we follow the string along, we get to this t. Now, it's actually facing down on the diagram, but if I wanted to make it and say, is it going left along the string or right along the string, which would you say? Hopefully you can see it would be right, yeah, because it's going towards the right end of the string. So let's, I'm just going to do a new line, but I'm still continuing with my same expression, plus t. Then we've got this one here, so that's minus t. And then we've got this 0.98 g, which is effectively going right. 0.8 g in this case. And add all that together, and you've got minus 0.72 g, because all those t's, in fact, just cancel. Okay, so it's kind of like just taking this right part of the string and kind of turning it upwards so that it just continues along to the right as if it had never gone around the pulley. And that's a perfectly acceptable thing to do. It's resolving forces horizontally along the string. Cool, so that's the force. Then let's think about the mass. So we've got the force of minus 0.72 g. And what else? Oh, hang on. What am I talking about? This is plus, isn't it? Silly me. That does make more sense. Yeah, so plus 0.72 g, that's equal to mass, which is 0.8 plus 0.08, so we've got 0.88 times acceleration. Therefore, acceleration is equal to 0.72 g divided by 0.88. And that's equal to the wrong answer because I made a few too many mistakes in this part, haven't I? 0.4, not 0.08. What was I thinking? Because this had a G in it, I foolishly was assuming it's a weight. Of course it's not. The mass is 0.4, the mass is 0.8, therefore the total mass is 1.2. If you don't learn from your own mistakes, at least you can learn from mine. Okay, there we go, 1.2. Okay, and that gives us a final answer of 0.6 g of the acceleration. So this whole system then, because it's a positive answer and we were taking horizontal and to the right as positive, this whole system is saying that this ball moves right, this ball or particle moves down, and the whole system is accelerating at an acceleration of 0.6 g meters per second squared. Great. So now, what's the time taken for B to reach the ground? B was this one. Time taken. Okay, so that's just solve that again, isn't it? Okay, so it all just relates to stuff we've previously done before. What's the initial speed of B? Starts from rest. What's the acceleration? I'm going to take down as positive now. So I'll call the acceleration 0.6 g because I know it's going down. S equals 0.5. T is unknown. S equals ut plus half at squared. It's all becoming nice and familiar now. Let me just rub that out so it's sort of a bit, so you can see that a bit more easy. S equals ut plus half at squared. We know u is 0, so it's just going to be S equals half at squared. Or in other words, t is going to be equal to the square root of 2s over a, which is the square root of 2 times s is 1, all over a, 1 over 0.6 g. Take the square root of that, and I'll write the final answer up here in red. That is about 0.412. That's the time taken. Cool. And the total distance travelled by A before it first comes to rest. Okay, so A is this one. Right, okay. So this is interesting now. This is where you have to do a little bit of, really quite a bit of thinking. So the first thing to think about is this. Why is A going to come to rest? A is here. This is let go, it drops, A is moving to the right. Why would it suddenly come to rest? So the reason it'll come to rest is because in this case we've got some friction. And friction has the ability to make something end up at rest, but only if there's no driving force which is overcoming the friction. To start with, there's a driving force, which is this, effectively the tension here in the string, which is caused ultimately by the fact that there's a string hanging here with a particle. So this particle's going down, this is being accelerated along, so it's got this acceleration, and then suddenly when this B hits the ground, at that moment, A will no longer have a driving force, because the string will become slack, right? So let me see if I can sort of, as best as I can, animate this. One moment. Okay, so I've removed the string, but can you just imagine that it is in fact still there? There's still a string connecting these two particles. Here's what's going to happen. This one B is going to fall. It's going to fall, get faster and faster, and then hit the ground. At exactly the same time as that happens, this one here, A, will also be moving to the right. It'll be going right. Okay. and it'll have been how far? How far will it have moved at that point? Well, it was 0.5 meters above the ground, wasn't it? So actually the case, realistically, let's not make it go along too far. Okay, well, the point is they've moved the same distance, and that distance is 0.5 meters. Okay, so it fell 0.5 meters. They both did. They both moved 0.5 meters, and the time taken for that to happen so far is this 0.412 seconds. So let's put in brackets here. That took 0.412 seconds. Okay, that's me with an S there, and B is not going to move anymore. I mean, it might bounce or whatever, but you know, for our purposes, effectively, it has B has no more influence on A. And this string, if you imagine the string was here, okay, it's effectively connecting here and then here. But now, if I bring the string a bit to the right here, there's nowhere for it to go on the other end, so it's going to become slack, right? So literally, by slack, I mean, you know, it's becoming a loose string in some sense, right? This particle A is going to keep moving. It hasn't got a driving force anymore, though. It's going to keep moving. And the slack string is just going to do whatever. So eventually, you know, this object A will stop somewhere. Let's say it stops around here. And then the green string could look something like this. It'll be, you know, a big mess of slackness. And, you know, it may still connect here. But the point is the string has no more influence. The string only influences this particle A while it's taut. So we've got these two parts of the motion. There's the first part, the 0.5 meters, and it took that long. And now we need to think about what's happening in the second part. So it's here. Okay, when the object's here, the A, what are the forces acting on it? Well, we've still got the frictional force horizontally. That's 0.08 G. Okay, we've still got, not that it's that relevant, but we've still got gravity, we've still got the reaction force to that, which is the same. But this force to the right no longer exists. It's gone. There's no more tension in the string. So what that means is the situation has changed from having an acceleration of 0.6 g to the right. Now there's an acceleration, or essentially a deceleration. It's 0.8 g to the left. Right? Oh, sorry, that's the force of 0.08 g to the left. And from that, we'll then figure out an acceleration. Okay, so let's find that out now. So now the total force on A has changed. It's now minus 0.08 g. And using that being equal to ma, which is the same as 0.4a, that implies that A equals minus 0.08 divided by 0.4 g, which is equal to 0.2 g. Okay, 0.2 g. So now let's find how far is it going to go with this acceleration of 0.2 g. So we'll say the acceleration is equal to minus 0.2 g. I want to know how far it's going to go. And when I say how far it's going to go, I mean how far it's going to go until the velocity is 0. The final velocity is 0. But then I'm still missing a bit of information. We still need something else. Well, we could potentially find the initial speed, right? What's the initial speed? So the initial speed is how fast was this object going? In fact, both of them, A and B, once they've travelled the 0.5 meters, how fast, are they going? So maybe we need to retrace our steps slightly. Put this on hold for a moment. Let's stick this up here, save it. Let's find how fast they were going. So they were starting at u equals 0. They went a distance of 0.5. Okay. The acceleration was 0.6g, and I want to know how fast they were going when that after all that happens. So we've got v squared equals u squared minus 2as. So therefore v is going to be equal to the square root of u squared, which is 0, that's easy, minus 2a times s. Oh, sorry, I've done the wrong version, plus here. Okay, so then that's 2 times a is 1.2g times 0.5. Stick that in the calculator, and you get 2.42487. 2.42487. Okay, and the reason I've used so many decimals is because we're about to reuse this value, so we want to make sure we've got as high of a precision as possible before we go and re-substitute it into something else. Okay, I've just lost my acceleration here. This was minus 0.2g, wasn't it, from before? Okay, so at 0.5 meters, it's got a speed effectively initially, of minus 2.42487. The final speed is going to be 0. We want to know how far it travels in that for that to happen, and the deceleration minus 0.2g. Then we use a formula appropriate to the case. Let's go for v squared equals u squared plus 2as. Therefore s equals v squared minus u squared all over 2a. Just shift that up a bit. And we're just going to be plugging these values in to find what our s is equal to. In this case, v is 0, isn't it? So this becomes even simpler. This is minus u squared all over 2a. So we're looking at getting 2.42487 squared minus divided by 2 times a, which is minus 0.4g. And we can see this is going to give us a positive number, which makes sense because we're looking at a distance to the right. Plug that in. What do we get? 1.5. Cool. We got 1.5. All right. So then that tells us that at the point where B hit the ground, A then kept moving for another 1.5 meters. Okay, under a different deceleration. So A was here, it was accelerating until it hit 0.5 meters, and then boom, A hits the ground, and now there's no more force pulling A along, and it's just decelerating under friction, and it decelerates and decelerates, and then eventually stops here. The total distance travelled by A before it comes to rest is therefore 0.5 plus 1.5, 2 meters. Done. Okay, so time for you to try some questions yourself. I've got 3 questions for you to try. Just take a look at this one first. Pause the video now. Okay, let's take a look at the answer. And second question of 3. Pause the video now. And your answer. Quite a bit of working needed for D there, but at least it's given to you. And then the final question, so nice cliff edge or table edge question. See how you get on. Pause the video now. And there's your answers.